Hello everybody, my name is Paul Abernathy and welcome to our Transformer series. We're at part 4 in the series. Today's episode, we're going to talk about secondary conductors. And that is the 10 foot, 25 foot, and unlimited. But on this episode today, we're going to keep it to the 10 foot secondary conductor rules. So it should be a pretty quick video in order to get you up to speed on the secondary 10 foot rule. Now, we're also going to talk about C1, that's 240.21C1, which is a very obscure rule, whereas the primary overcurrent protection that protects the primary side of the transformer could also serve to protect the conductors on the secondary side of a transformer. It is very unique, and we'll look at it very briefly, but only applies to two different types of transformers. Any other application, you're going to have primary and secondary protection of those primary conductors and secondary conductors. Okay, so there's a couple things we want to talk about at this stage. We're going to assume that you watched the first video in the series, part 1. Now, part 1 is going to teach you how to size the primary and secondary current ratings of a transformer. If you don't know how to do that, you're going to get lost. You got to go back and watch part 1. Once you understand those formulas and some of the shortcuts and tips that we give you there, then you move on to part 2. Now, part 2 is going to talk to you about how to size the primary overcurrent protection and the secondary overcurrent protection. Now, this overcurrent protection is to protect the transformer. Now, it might also protect the conductors on the primary and secondary, but its primary role is to protect the transformer. And you need to go back and watch part 2 to fully get an understanding of that. Okay. Part 3 in this series, we're going to talk about conductor sizing for the primary as if you weren't using any tap rules. And then we're going to go into the nuances of using the tap rules under 240.21B3, which is utilizing what's called the primary plus the secondary 25-foot tap rule. And that is a unique tap rule that might save you a lot of grief if you possibly undersized your primary conductors for some reason and you want to see if you still meet the rules of the tap rule. Okay, so go back and watch that. If you haven't watched those and you're trying to jump into this video, which is part 4, you're going to have a hard time. Okay, so we're going to assume that you already did that. Now, they're going to give you a couple givens here to kind of bring us up to speed. So assuming you watched part 1, 2, and 3, you understand that we're dealing with typically a 75 kVA transformer. Now, we're going to give you some examples today where it really doesn't matter the kVA because we're going to show you how to do multiple sizes for the secondary. But just to give you the lay of the land on what we've done to this point, we know that the primary current rating of a transformer of the 75 kVA is 90 amps. The secondary secondary current rating of the transformer is 208 amps. Okay. Now, in part 2, we sized the primary overcurrent protection of that transformer at 125%, but we could have gone all the way up to 250%, but we did it at 125%. And since it didn't correspond to to a standard size device, we went up to 125 amp rated device. Okay, and we can do that because we don't exceed the 250% maximums that are afforded in table 450.3b. Okay, again, you need to go back and watch that part, okay, part 2, if you didn't understand any of that. Okay, so as givens, 125 is our primary protection. And incidentally, it is also protecting our primary conductors as well. Okay, because we took our 90 amp primary rated current and took it at 125%. And that was 112.5 amps. We went to find a conductor that had at least that ampacity rating. We found that we had a 2 gauge that was good for 115 amperes. And yes, since a breaker doesn't correspond, we can protect it with a 125 amp rated device. So that primary overcurrent protection that was protecting the primary is also protecting the primary conductors. So we're good to go there. Okay. Now we're moving on into the secondary conductors, okay? And we're moving away from the tap rules and moving into secondary conductor rules, okay? So that's where we want to pick it up right now. All right, so let's look here and some of the things that we know. Again, we had a 90 amp primary current rating, a 208 secondary current rating, 125 amp primary overcurrent protection, and then based on our original calculations, based on the 125% of the secondary current rating, this was a 308 a 300 amp rated overcurrent device, and yes, it can protect the secondary. That's fine. It can't exceed 125%. And if it didn't correspond, then you go to the next size up, and that's what we did, and that's how we ended up with a 300 amp. Now, let's talk about reality. So this is what you do in an exam, right? In the real world, let's come back to me real quick. In the real world, we're going to have loads that have to be calculated. So the engineer is going to calculate the loads, the branch circuits, the feeders, all of the loads that are associated on a panel board. That panel board is now going to be sized based on whatever the loads are. So let's say in our case, that for getting a 75 kVA transfer, say we don't know what we need. We don't know. So the engineer is going to say, okay, well, I've got 180 amps of load. He's figured it all out, whatever that might be. He's going to put a 200 amp panel in. Now, that's what he calls for. Okay. Well, can a 200 amp panel be supplied by a 75 kVA transformer? Absolutely, because the secondary current rating was 208 amps. So I can get 208 amps out of that secondary of that transformer. Okay, so he puts a panel board in, and he puts a main breaker in that panel board, which is the secondary conductor protection that we talked about in part 2. Okay, but it doesn't have to be up to as high as 125%. In this case, it's not. It's less than that. It's fine. Okay, perfectly fair. You can go up to 125%, but you don't have to go up to it. So on an exam, if it asks you for that, you're going to go up to the 125%. But in the real world, if it's a 200 amp device, let's look at the graphic. That way I'll make it a little simpler. If this right here was 200 amps, okay, then these conductors right here that terminate into it would have to be rated for 200 amps, and that would be a 3/0 copper. Okay, again, we're always assuming copper unless stated otherwise. All right, and so that would be the design, and this transformer could handle this with no problem. No problem. Even if this was 75 kVA and they used the 300 amp device here, then it would be 300. Then these conductors would have to be sized based on 300 amperes, and that will result in a 350 kc mil conductors, because a 300 only has 285 amps, and we can't use the next size up rule here. And you're going to see that as we look at the code a little bit, but you can't use the next size up rule like you can on the primary side. The secondary side, these conductors have to have the full ampacity of whatever the device or the equipment rating is. Okay. In this case, if it was a 300 or a 200 or whatever it would be. Okay. So we're just kind of taking some things for granted now. All right. So we're sizing these conductors here. Okay. Now, the other thing to remember, I could have an overcurrent protection right here where they get their source from. And if that's the case, then these conductors don't have to be limited to the secondary conductor rule. They could be limited to whatever the rating is to handle the load, and we're basing on the load that needs to be on it. Okay? And if that's the case, then they are actually feeders that are going out, and I would have to apply Article 215 to apply it. It'd be 125% of the continuous and 100% of the non-continuous. But these are secondary conductors. There is no overcurrent protection right here, so we do have some length limitations that we have to worry about under the secondary conductor rule. Okay? All right, so let's do that. So let's go on and now go on and look at the 10-foot secondary conductor rule. Okay, well, actually, before we look at this one, let's go knock out of the way the first one, C1, which is the one that I said was very obscure. Well, before we do anything, let's read C, because here we're dealing with secondary conductors. Number 1, it says a set of conductors feeding a single load, okay, and that would be like feeding our panel that we just looked at. It says, or a set of conductors feeding separate loads, so I could have multiple panels being fed from a single transformer. That's okay, as long as that transformer is sized properly to handle whatever the load, the secondary current can actually handle it. Okay, it says, shall be permitted to be connected to a transformer secondary without overcurrent protection at the secondary. Okay, so what are we saying here? So, oops, go back to the video here. Here. So it's saying right here, I don't have to have overcurrent protection right here. All right, that's the whole purpose of this secondary conductor allowance. But if I did have overcurrent protection right here, then I would just treat the conductors on the load side of this protection as feeders, and I would size them to handle the load or whatever. But here we're trying to utilize these secondary conductors which have no overcurrent protection right here. The overcurrent protection is right here, okay? And this protects the panel board if it's a lighting and appliance type of panel board or lighting and power under 408.36, okay? So that's what we're dealing with that. All right, so let's go back and look at the rules for C1. Yeah, let's finish reading what we're working on. Okay, so it says that, I could have that secondaries feed multiple loads. Shall be permitted to be connected to a transformer secondary without that overcurrent protection, as we just talked about. It says, as specified in 240.21 C1 through C6. So you have 6 different options here for these secondary conductors. It reminds us, again, that the provisions of 240.4b shall not be permitted for transformer secondary conductors. Okay? What does that mean? Well, if you remember in previous series, another parts of this episode, that I cannot use the next size up rule on the secondary conductors. I can do it on the primary, I can do it on other aspects of the code, but I cannot do it here because I have to size them full size based on whatever the device that I terminated into. And you're going to see that rule here in a second. So again, I can't use the next size up rule that's found in 240.4b. Okay? All right, so that's the rule that we have to remember for that. Now let's look at this one. Here's the first one. All right, so 240.21c1, this one right here. This is a weird rule because this is one that allows the conductor supplied by the secondary side of a single-phase transformer having a 2-wire and it has a single voltage secondary, or a 3-phase delta-to-delta connected transformer having a 3-wire single voltage secondary. They shall be permitted to be protected by overcurrent protection provided on the primary, the supply side of the transformer. Okay? Provided, again, that this protection is in accordance with 450.3, and we've shown you how to do that in part 2 of the episode. Okay? And of course, and it does not exceed the values determined by multiplying the secondary conductor's ampacity by the secondary to primary transformer voltage ratio. Okay, so we're not even going to get into that because this does not matter unless you're dealing with a single phase 2-wire with a single voltage secondary, or a 3-phase delta to delta connected transformer with a 3-wire secondary that has only a single voltage like a 480 or 240. Other than that, it goes to remind you right here. It says single phase and multi-phase, 3-phase transformer secondary conductors are not considered to be protected by the primary overcurrent protection device. So it only applies to these unique transformer setups. Okay, so that is so obscure that you're not going to see that on any code exam. Yes, you might deal with it if you're doing a delta to delta. Then it might, and it's a three-wire output, and it's only one voltage scheme. It might happen. Okay, then that primary. Now, it doesn't mean that you can't have overcurrent protection on the secondary. It's just saying that those conductors can be considered protected by the primary under this rule, as long as you meet that secondary to primary ratio and all the multiplication that's qualifying it here in this C1. Okay, that's most we're going to talk about that one. Okay, so if that's the one you run into, it just simply follow the rules that are written right here. It shouldn't be complicated. Now we're going to move on into this one: transformer secondary conductors, dealing with 240.21c2 for today. Okay. Now we have 4 different rules here that we have to follow in order to be able to utilize these conductors up to 10 feet without overcurrent protection right here where they get their source, which here is the X1 and all that right here. So we're going to deal with these conductors. Now, incidentally, we are not going to be sizing the grounded conductor today. We're saving that for the same video when I talk about how to calculate the supply side bonding jumpers, the grounding electroconductors, and all of that. We're going to save the sizing of that. So that's going to be another series. Okay. So you have to watch that once we get to that. Okay. We're not going to size the supply side bonding jumper in this one today. We're just dealing with these conductors in the secondary conductor rule today. Okay. 240.21c2. Now let's do some assumptions here. What if we did say the load was, under 200 amps, and so the engineer sized this at 200 amp? We don't know what the transformer's kVA rating is yet because the engineer's sizing it all. But in this case, this is a 200 amp rated device right here, and the load was less than 200 amps for whatever reason, 200 amps of non-continuous. So he's done this, and this is our load. Okay, let's just take it at that. These conductors are sized based on the 200 amp device. And we're going to see that right here in a minute. but that's what we've done. So these are 3/0 and they're good for 200 amps. Okay, that's based on the engineering design. Then he selects the type of transformer that needs to be able to handle the loads on hand, to be able to, based on whatever this device is. So in this case, a 75 kVA transformer, which has a 208 secondary current rating, is perfectly okay here. Could it be larger? Could this have been a 150 kVA transformer, but still only have a 200 amp device here in 3/0 conductors? Absolutely. You don't have to, because I could have had the options to have multiple panels being fed by this transformer. Okay, so just keep that in mind. All right, so let's look at what we got at hand. Now let's assume, forget the 75 kVA at this time. No, let's go on and do the 75. So we're assuming a 75, the engineer designed it, but he said this panel is only going to have a 200 amp device. And this is right here, this is going to be a 3/0 for argument's sake today. All right, good for 200 amps. Okay, number one, it says the ampacity of the secondary conductors, these right here, are sized not less than the combined load supplied. Okay, so whatever his load calculation is, let's say his load was 180 amps. Okay, you think, well, wait a minute, isn't that more? But then it goes on to say, well, and rated not less than the equipment containing the overcurrent protection device, or whatever the equipment might be, supplied, or not less than the rating of the overcurrent protected device at the termination of the secondary conductors. So in our case, if this was a 200 amp device protecting this panel board as well under 408.36, then this is 200. That's the limiting of the load. It's to 200 amps. This conductor here is good for 200 amps because it's a 3/0 copper. So everything's good. So we met this first rule. That's all fine. Okay. Now, incidentally, if we had followed our base calculation and we said that this was based on a 300 amp device, yes, it exceeds what the potential output of this transformer would be, but that doesn't necessarily mean the load actually exceeds it. I can always have a larger device as long as the load doesn't exceed it, and we have to provide a calculation accordingly. However, that would result in these conductors having to be rated for whatever this device was based on this rule as well. So these would be 350 kc mil. Or I guess I could parallel them as well and end up being smaller. But for a single one like this is shown, these would be 350. So you kind of see how that works, all based on whatever this device rating is. Okay, so that's the first one. Next, secondary conductors don't extend beyond the switchgear, switchboard, panel board, disconnection means, or control devices they supply. Well, this is what it supplies, and it terminates right here. They don't go anywhere else. So this rule is met. Okay. If this just had been an enclosure with a disconnect in it, and just one disconnection means, again, as long as it doesn't leave this enclosure, this panel board, or whatever this disconnection means, then it's okay. It stops right there. Next, 3. It says raceways used to enclose the secondary conductors, and they extend from the transformer to the enclosure, of the enclosed switchboard, switchgear, a panel board, or control device, or to the back of an open switchboard. Okay, so in this case right here, they are coming in, and this is all a raceway. All right, this is EMT. This is a tubing, but it does, under dot 2 of its definitions of EMT, does state clearly that it's a raceway. And this is FMC, flexible metal conduit. It is a conduit, and it is also, under dot 2 of its definition, is indeed a raceway. So this rule is all good, and this satisfies it, and so I could have a setup just like this. Okay. Incidentally, it does not say that this could not be PVC. Okay. It doesn't say that it has to be metallic. All right. Just kind of throwing that out there. All right. Now, let's go on to number 4. And number 4 says, all right, now, let me tell you right now, let me come back to me real quick. When it comes to number 4, this is a field installation rule, and it's really never going to come into play. I mean, I guess it could, so you need to know how to do it. But most of the time, I don't really see where this really comes into play. Now, I guess it could come into play if you're using this 10-foot secondary conductor rule and you have a lot of conductors, a lot of transformers that are being supplied, I guess. I guess that's when it could come into. But just go on and look at the rule, and we'll show you. But I don't, for the life of me, think that it's worth considering. But you do need to look at it. So we'll go on and do it. So here's what it says. For field installations, The secondary conductors that leave the enclosure, this is the enclosure, where the supply connection is made, which is right here. Okay, rating of the overcurrent device of the primary, right here, which was 125 in our case, shall be multiplied by the primary to secondary voltage ratio, which again was 480 divided by 208, which is that 231. Okay, that we deal at, and again we rounded it up, 0.5 and higher we round up, so it was 2.307, I believe, or something like that. So we rounded it up to 2.31. That is our primary to secondary voltage ratio. And that resulting value, which is, in our case, 125 multiplied by 2.31. So let's do that. 125 times 2.31, and that is 288.75. Okay, so that resulting value can exceed the ampacity of the secondary conductors by 10 times. Well, look, no matter what we decided based on our loads, whether this was a 200 amp or a 300, both would comply with this transformer. But either one, if you take their value of the conductor that's supplying it, for in this case, let's say it was the 2-aught, and it is good for 200 amperes. If I take the 200 times 10, that's 2,000 amps. Well, that 288.75 is no way exceeding the ampacity of these conductors by 10 times. That's not an issue. And in this case, if it was 300 and those conductors are 350 kc mil, then that's 310 amperes times 10, and that is 3,100 amperes. Again, there's no way, okay, this value that we calculated is exceeding the ampacity of these secondary conductors by 10 times. So for all intents and purposes, you're not going to run into this. Now, there might be some obscure thing that you run into it. I don't have time to go over all potential issues which may come to that. Just know how to do it. And I just showed you how, and that's not a problem. So if you meet 1, 2, 3, and 4, which we do here, then these conductors can go up to 10 feet. Okay. And it's not 10 foot of this raceway. It's 10 foot of the conductor. Okay. That's the 10 foot secondary conductor rule. Okay. And you're going to be fine. All right. So that's a lot of info. Overwhelming info. So again, go back and watch part 1. Learn how to calculate that primary and secondary current rating. Definitely learn how to size the overcurrent protection for the primary and secondary of the transformer. Watch that series and then understand in part 3 where you're sizing the conductor and understand that you have to protect the conductor at its ampacity. However, we do have some beneficial things that come in tap rules under 240.21b3. You got to go back and watch that. Now you're getting beyond that, and we're not dealing with the tap rules. We're dealing with secondary conductor rules, and we're trying to find out what the length is of that secondary conductor. And we have limitations where we don't have overcurrent protection at the source of those secondary conductors on the secondary side of that transformer. Okay, so we can go up to 10 feet under this rule. And we saw what you have to do in order to be able to meet this rule. So hopefully you learned something about the secondary conductor rules. Again, we looked at C1, which is really so obscure. Most any other occasion, you're going to have primary and secondary protection of those conductors on the primary and secondary side of a transformer. But remember, if you happen to run into a single phase transformer dealing with a 2-wire secondary and you have 1 voltage value, then the primary could protect those secondary conductors. Okay. If you're dealing with a delta to delta and it's a 3-wire secondary with a single voltage value, like a 480 or whatnot, okay, then the primary might protect the secondary conductors. Any other transformer situation, primary and secondary protection, you got to have it. Okay. So hopefully that was educational for you. We're going to go into part 5, which we're going to then deal with the 25-foot tap rules for both an industrial application as well as the general 25-foot tap rule. But if you have any questions on this 10-foot secondary, and I keep saying tap rule, those are secondary conductor rules, not tap rules. Okay, taps fall under B for feeder taps. I know they're the same and it's okay to use each and or, but try to get yourself, and I still struggle with it. Tap rules, where you're tapping a feeder. Secondary conductor rules, you're not tapping a feeder. You're applying the secondary conductor rules. Okay, kind of play with it. I gave you some examples here of how they might work out for you in this scenario. So if you have any additional questions, email me at info at masterthenec.com or info at Electrical Code Academy, just like it's spelt right there on the screen. And you can email me any question you want, whether it's transformers, whatever you need. If you don't know how to calculate the ampacity values for conductors based on adjustment and corrections, make sure you go watch that video on what's called derating demystified, because I cover all the things that deal with 31015 B2A and B3A and all of those things for adjustment and corrections, which could come into play here on secondary conductors depending on the ambient temperature or the number of current carrying conductors that you're dealing with. Okay, we did not size the grounded conductor in this episode. Okay, just the secondary conductors, okay? We're going to cover the grounded conductor in a later episode, as well as the supply side bonding jumper, the system bonding jumper, and all those type of things, okay? Don't worry, we're going to cover it all, okay? You got to watch all the series. You see the ticker below? Go to the website. Watch the videos. You can get to more videos than our website has a certain number of videos, but if you want to watch them all, then you go to our YouTube channel and you can get them all. You can even listen to our podcast through the actual YouTube channel. Okay, if you want to listen to them that way. But our podcasts are also available on Spreaker. They're available on iHeartRadio. They're available on Spotify. You can listen to them directly from the website. We have a little app there. You can download the app for your phone from Spreaker or whatever, Spotify. Just search for our episodes, Master the NEC, and you'll be able to get them. Okay, so till next time, stay safe. Oh, Facebook. Go to our Facebook page and join our Facebook group if you're preparing for an exam. It's a great resource for you. Okay, that's enough. Till next time, stay safe, God bless, and stay tuned for part 5, where we're going to go over 25-foot secondary conductor rules. Till next time, God bless.